Okay, this is part 3 for section 4.3, so this will wrap it up. And I have a final example that's a little bit different at the end here, but before that, we're going to look at one final rule for kind of zeroing in on roots or zeros, and that is Descartes' Rule of Signs. So let's look at that. Okay, this will be a way to kind of get an idea of how many negative and positive roots we might have. It's not going to tell us what the roots are, but it'll help us to narrow down our search when we're looking for roots and factors. So I'll have an example of that in a minute, but let's look at the rule. First thing you do is just count. You count the sign changes on the coefficients as you go from left to right in the polynomial function. So count sign changes, they call it. We'll see how that works in a minute. Okay. Again, you're just going from left to right, looking at the signs of the coefficients, and anytime there's a change, that's a count. So you keep a tally. The number of times they change, that's going to be the number of positive real roots. So this doesn't apply to complex. So this is a way to get an idea of how many positive roots we have. There is one thing here. That would be the maximum. So it could be this number of roots or an even number less. So for example, if we had 3 changes, we could have at most 3 positive real roots, or if I take an even number from that, which would be 2, 3 minus 2 is 1, or we could have 1 positive real root. That's kind of how that works. Okay, what about negative roots? A little bit different. Kind of the same idea though. But what you're going to do here is count sign changes but instead of x, it's going to be p of minus x. So in other words, replace x with minus x, and particularly with cubes, you're going to wind up with a negative, with a sign change when you cube a negative, that kind of thing. So put the negative x in, refigure the polynomial, and then do the same thing here. Whatever the number of sign changes is, in this case, that'll be the number of negative real roots. And again, or an even number less than that. So again, if I had 4 sign changes, then I could, in this case, I could have up to 4 negative real roots, or I could have 2 negative real roots if I took away an even number from that, which would be 2. Okay. All right, so let's give it a shot. Let's pick a function here. Okay, so there's our function. The first test is real easy. Just look for sign changes. I have a positive 1 here, and that changes to a negative. That's a sign change. When I go from here to here, this negative, then we're changing to a plus sign. When I go from here to here, there's no change in the sign. It's still positive. That's 1, 2 sign changes. So I have 2 real positive roots. Okay, and reducing that by an even number, since the smallest even number is 2, that would be 2 minus 2 is 0. That doesn't work. You're going to get a count of some type, so 2 is as small as we can go here. Okay, so now we want to check for negative roots. So what we want to do here is look at g of minus x. So the first thing we want to do is put negative x in place of x. And then let's figure out what that is. That's still x cubed, but a negative times a negative times a negative, that now is going to become a negative x cubed. And this will be right here, positive x squared times a negative 6, so no change there. Over here, positive 3 times a negative, we have a change, and then plus 10. One thing you can notice with this, using this rule, when you substitute a negative x in to a function, everything's going to stay the same except where the degrees are odd. If you have an odd degree, you're going to have a sign change. Even degree, no sign change. Odd degree, 1, we have a sign change. So that should make it easy. All right, so how many sign changes do we have? Start off with a negative, go to a negative, go to a negative, no change yet. I only have 1 change right there from a negative to a positive. That means I have 1 negative real root. And that's how it works. Okay, so it's interesting, but let's go ahead and use it now with a couple of the other things we learned in this section, see how we can put all this stuff together. So here's my function. I've got a description of what the roots look like, and by the way, there's the degree, so I know I need 3 roots. And that's what I've got here, 2 real, or 2 positive and 1 negative root. Okay, what else can we do? Well, we could try the 1, negative 1 test. So let's try the 1 test. Maybe we can find one of these real roots, real positive roots, real easy. If you remember the 1 test, we just add up the coefficients. So what do we have here? 1 plus a minus 6 plus 3 plus 10. Okay, that does not equal 0. What do we have here? 9, 10 minus 6 is 4. Since that does not equal 0, 1, not a root, so we can't get that. Let's try minus 1 test. Okay, if you remember on the minus 1 test, you're going to change the sign of any term with an odd degree. So instead of a 1, that's an odd degree, I'm going to use a -1. That's an even degree, doesn't change. So we're just changing the sign of the coefficient on the odd degreed terms. Still doing the same thing otherwise. That's an odd, that's x to the 1, so instead of +3, that's a -3. And for the coefficient, nothing happens. Okay, 1 minus 6 minus 7 minus 10 plus 10, that equals 0. That means -1 is a root. So we have a root, and as a matter of fact, that's a negative root, so we found the one and only negative root. For positive roots, let's go back now to the rational zeros theorem that we had, and we'll use it. That was the one where we're looking for P over Q, where P are the factors of the constant. So if we look at our function here, the constant is 10. So what do we got? Plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10. And Q were the factors of the leading coefficient, which is a 1 here. So let me change this. We'll find P over Q in a minute. This is P, and then Q is going to be plus or minus 1. All right. Right off the bat, we need to note one thing. According to the Descartes Rule of Signs, we only have one negative real root, and we already found it. It's -1. So that means we can't have any other negative roots, so that means all of these can only be positive. And if we're positive here, we're dividing by 1. These are our possibilities. But we can limit that list even more because we discovered up here the 1 test failed. So that's gone. So right now, I know g of x equals x plus 1 times some other things. So -1 is a root. Well, I only have 3 to test. So probably one of the easiest ways would be back to synthetic division. So let's test this. If 2 is a root, then let's see what we get here. Put in our coefficients. 1, -6, 3, and 10. Again, draw the line, bring down the first one. 2 times 1 is 2. Add these up. 2 times 4, that's -8. Add these up. Multiply these, that's -10. Add these. That's a 0. Since that's a 0, that means 2 is a root. So now I have if I wanted to look at factors. Okay, so we found out 2 is a root. Let's check 5. We only got to find one more. We only have 2 positive roots. So if 5 fails, then we know it's 10 and we're done anyways. Okay, same thing, bring down the 1, 1 times 5, -6 plus 5, -1 times 5, add these up, -2 times 5, that's -10, add those up, 0, Guess what? 5 is a root. So we got it. 1 negative root and 2 real roots. There they are. So there's a good example of using all of these different things together to zero in on roots. All right, I got one more kind of a different problem, but something you'll be asked to do, and that is, if you know the roots of a polynomial equation, how do you find the actual equation? We did this earlier, but this one's a little more tricky, but the idea is the same. What you want to do is, if you have the roots, like here, convert them to factors and just multiply the factors together, and that's how you do it. So let's take a look at an example here. What I want to do is find the polynomial and here's the roots. -2 and 1 minus I times the square root of 3. So there's 2 roots. However, we have some conditions here. The polynomial is degree 4, and all real roots are shown. So these are all the roots. Okay. It looks like we have a problem here. If it's a 4th degree polynomial, we're going to need 4 roots. And according to this, the roots are shown, all the real roots are shown. Okay, let's zero it down here. I have a root of -2. I have a complex root. But if you recall, whenever you have a complex root, the conjugate is also a root. They come in pairs, so this is also a root. Okay, now I'm up to 3 roots. I still need 4 roots, but if all the real roots are shown, what does that mean? It means this root is a multiplicity of 2, so it appears twice. So there's my 4 roots. So to find, let's call it P of x, we're just going to simply multiply all these together. That's going to be x plus 2, x plus 2, and then here we got to be kind of careful. Remember, if this is the root, it's minus that, so in other words, like here, x minus a -2 is x plus 2. So if that's the root, it's x minus that. So I'm going to start by putting the parentheses inside here. And then the other point would be x minus this one. If I don't put the parentheses in here, I'm going to miss this sign when I multiply this in. It's going to look just like x minus 1 minus square root of 3i. That's not what this means. We're subtracting this entire root, so therefore the parentheses. I'm not going to do the whole thing, but multiply these two together. You're going to get that. And then we're going to have to convert these, so that's going to be minus I, or minus 1, and then minus a minus plus I times the square root of 3. And then this one's going to be minus 1 and minus times a minus or I'm sorry, minus times a plus will be minus. So there's a lot of work here. You got 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications, and you got to add up all those like terms and come up with a final here. I'll write down what it is, and you can try it yourself. It's a lot of time. But if you multiply these two together, you're going to get x squared minus 2x plus 4. Once you simplify all of these terms. And remember, at the end, you're going to get an I squared, so you're going to want to convert that to a minus 1. Anyways, you should be able to go from here to here. And then finally, if you multiply these together, again, that's a lot of multiplications. With that one, you got 3. With this one, you got another 3. Here, another 3. That's going to be 9 different terms. Again, you're going to have to add up all the like terms and stuff. But you can see from the very first multiplication, you're going to get an x to the 4th. So that's our 4th degree polynomial. And if you figure all this out, you should come up with this one right here. Unless I made a mistake, that's the polynomial. And that wraps it up for 4.3.